So before I begin, I would like to thank my colleagues at Argonne, Kevin Gasperich and Hyun-Duk Shin, who participated to this work. It was done as part of the Center for Predictive Simulation of Functional Material using the QMC pack. So the problem that I want to use as an application problem to try to understand a little bit what we can access and what we can do with quantum Monte Carlo method is the lithium cobalt dioxide. This is a very old material, and it has been widely used as a cathode active material. It's fairly common, or at least it's fairly understood its structure. It's an ordered Rock-Salt phase. And basically, DFT or DFT+U has been very successful at describing its properties and also at predicting the band gap. However, like for everything, once you start playing with DFT+U, once you get one property, you're going to mess up other properties. For instance, DFT+U may get the correct band gap, but it might also underestimate the intercalation voltage and overestimate the lithium order-disorder transition temperatures. Also, this is the value of U that was conventionally accepted amongst DFT practitioners. But yes, it gives you the correct insulator behavior, but shows the transition into a high spin state, which is in stark contradiction with the experimental measurements. So I decided to take this very, very classical material, or at least very important industrial material, and try to apply quantum Monte Carlo to it to see what we're going to get out of it. So just from a DFT+U standpoint, when we look at it, we see that the you can see them, right?
Yes, we can see them.
Yeah, okay. So from a point of view of the density of states, projected density of states, once we start looking at how the T2G states, basically where we are interested in the transition from the band gap, goes to this cobalt EG states and the cobalt T2G, and this is where we expect the gap to be. But when we look at the PB, projected density of states, the PB+U at different values, we start seeing that there is a strong PD hybridation that is shown for large levels, for smaller levels of value of U. But the moment we start increasing the value of U, everything becomes a little bit smirkier, and this T2G and EG seems to be far from each other, and they are far from the edge of the balancing conduction bands. So it becomes very hard just from a DFT point of view to understand or to decide where the electron is promoted from or to, and the DFT+U cannot describe really the ideal electron distribution from strongly correlated lithium cobalt dioxide. So what we tried to do here is also try to see at the charge density and seeing the effect of the value of U on this the EG and the T2G orbitals. And we can see here that what happens is that once we add that value of U by promoting the D electrons, we start to have a charge accumulation and depletion of the T2G and the DXY and the DXZ and the DZY states. But basically, we see that it is kind of a sensitive type of effects on the charge density and the occupation levels that we can see once we start adding a value of U. So once we try to compute the band gap, of course, if we change a functional, we start getting more or less whatever value we want. From LDA+U to hybrid more recent functionals, nothing really is close to this value of the 2.1 to 2.7 experimental value that we can have. So the question is, can quantum Monte Carlo fix this problem? Of course, I'm not going to go into details of quantum Monte Carlo, but diffusion Monte Carlo in itself is very useful in the sense that within the fixed node approximation, we have the method is variational and upper bound to the exact nodal surface. So we know that if we have the correct nodal surface describing the problem, we will have the exact solution of the system. But of course, the whole challenge becomes, do we have the correct nodal surface to describe this problem? In this case, we choose the nodal surface to be made of this Slater-Jastrow functional, where we describe the Jastrow function that are going to give us some type of dynamic correlation into 1, 2, and 3 body Jastrows. And the antisymmetric part of the Jastrow is going to be defined by either a DFT or a Hartree-Fock wave function. In this case, we're going to choose the DFT wave functions. So One additional tool or knob that we use in DMC to be able to optimize the nodal surface has traditionally been to just use the DFT+U as a starting point, and we can change the value of U. And because the method is variational, and it's really important to remember that it's variational, we can find these minimum energies like here for the nickel oxide. Of course, when we have DFT, it's not the case because we are just promoting electrons to the D band, so nothing happens. But in the level of QMC, we do have this nice values here of U, and you can see even in cases like nickel oxide, either we pick LDA+U or GGA+U, they reach the same energy for both of them. We can do exactly the same type of trick of having one knob control of the nodal surface by playing with the hybrid functionals and playing with the exchange and correlation the exact exchange concentration, and we get similar behaviors. So we try that on the case of the lithium cobalt dioxide, and this is absolutely not what we find. What we find is rather weird behavior. So we start increasing the value of U, and it's the black dots that we see here. We don't find any minimum, but once we reach a value of U equals 10, we start having magnetization happen, and the system becomes magnetic, which is absolutely not the case. And the only way to be able to get something is by constraining the system. So we force the system to not be magnetic. Then we find this value of minimum U here around 11, which is highly unusual. And of course, the value of U equals 11 makes almost no sense. But we decided just to go with it and see what that means in this case. So once we start doing the band gap calculations using this value of U, even at the DMC level, we are pretty off. Even if we do so for a direct band gap, we are at 6.3 eV instead of 2.1 eV. And the only way that we can find, and this is of course by taking care of finite size effects and finite size correlations, and by extrapolating everything, we still have these numbers that are significantly off. And the only way that we can get closer to the real band gap, or at least to the experimental band gap, is by thinking that there is some indirect band gap between the gamma and the endpoint. And this is absolutely not satisfactory. So something is off with the nodal surface. And this is where we try to improve a little bit better the nodal surface to see what's going on with the system. So for this, we use selected configuration interaction, and this is a similar method that Claudia Filippi presented yesterday. So I'm very happy that she did most of the work in describing the method. But just very, very quickly, for selected CI, we choose the CIPC version of it, and you can take any version of selected CI, will do more or less the same thing. The reason why we pick CIPC is because we do the evaluation of the PT2 or the second order perturbation theory at each step. So it compacts, it gives us a more compact wave function, so we can deal with DMC with larger wave functions. But basically, we start from a Hartree-Fock or any type of ground state energy or determinant, and we start doing all the single and double excitations at iteration 1, and we just select a criteria that will just either enter some determinant that are going to contribute to the energy beyond some level. The ones that don't are ejected, and we enter this determinants into the wave function, and we diagonalize again. At iteration 2, we do that again, and now we have from the single and double excitations, we start doing single and double excitations will correspond to triple, quadruple, etc., and then we can access to the full space. If the selection criterion that we use is extremely small, then we get the exact full CI limit. But if we put something slightly larger, we can just get the biggest contribution in our system. This is great, but we can also add the correction to our system, and then we can converge even faster in terms of energies. So this is very, very useful type of system to be able to get compact wave functions. And of course, the method remains exponential, and we are limited to smaller systems, but I will show you that even smaller systems, we can get a lot of physical information from it. This was done for molecules a long time ago, and now multiple groups are using it. This was done for molecules by the Caparel group in France. But since then, we have implemented it for solids by introducing Slater-Condon rules describing how we can do selected CI or full CI in a solid, taking into account all the different symmetries and K-points. We have used also density fitting to reduce memory requirements, so we don't have those full 4-electron integrals that are very costly. And of course, we added also the K-point symmetries to be able to reduce even further the size of the excitation. So we can do all this within different K points. And when we applied it to the carbon diamond recently in 2020, we were able to reach the thermodynamic limit for carbon diamond within a multi-determinant wave function that is completely converged to the full CI limit using twist averaging and using also just at the gamma point. So this works well. And how does it apply to our problem? So lithium cobalt dioxide is not carbon diamond. So we were limited to a primitive cell that had only 3 times the simulation cell. So this still is about 400 orbitals that we are using. So this is still expensive, and 90 electrons. So imagine doing this for a full CI, and this is what we are trying to do. One thing that plays on our side is that when we do the QMC evaluation, we only work on the occupied orbitals. All the unoccupied don't matter. So we do the full calculation with periodic boundary condition and all the K-points converge within 405 orbitals, but then we truncate them to the first 200 when we do the selected CI. As Claudia explained yesterday, we are able to do the ground state and the excited state by adding the same weight when we do the selection process in the selected CI. So we know that we have the same weight on the ground state and the excited state. And this is very important because when we see the convergence, yes, we are far from converging our system to the full CI limit, but we see that here we have the energy, the variational energy, and here we have the variational energy corrected from PT2. In the lower curves, we start seeing that there is some type of monotonic slope that are happening first, and then that the gap, the difference between the ground state and the excited state, seem to be fixed, which is very good for us. That means that we are introducing really the same weight, or at least the same level of correlations when we add multi-determinants to the ground state as we add to the excited state. And I will say that in this specific case, what it means is that we are degrading a little bit the selection for the ground state in order to be able to get a good description also for the excited state. So this works really well, or at least this is what we think. And we try to analyze, and we stop the convergence at 5 million determinants because this is the max that we can use in QMC pack our code, which is already a lot of determinants, but this is what we decided to stop at. From here, we tried to have a little bit of understanding of the physics of the problem, and we started looking at the reduced density matrix for this system based on the PDE orbitals of the system. And here we can see that when we do a difference between the excited state in single determinants minus the ground state, these are the occupied orbitals here, and these are the unoccupied levels. We see that when we do a band gap calculation, we are basically promoting electrons from a deep orbital here to a larger orbital in the unoccupied valence part, which is not what we are expecting to see in this class of materials, because we're expecting that the band gap is created between the HOMO and LUMO, or at least a diverge between HOMO and LUMO band gap. However, the multi-determinant part seems to show that the band gap is actually originating from the contribution of multiple orbitals here and getting closer now to that band gap here to this unoccupied-occupied border, which is a little bit better than the single determinant, the single determinant image that we had at the beginning. So this is good. We can start thinking that the multi-determinant is correcting a little bit the system, and we are happy about it to some extent. So what does this mean if we are comparing now what are the effects of this multi-determinants on our wave function? So here for the ground states, I am doing the difference between a multi-determinant one-body RDM minus the single determinant one-body RDM to try to see the occupation, how do the orbitals behave? And here we see that we can see a little bit of movement here in the diagonal, but really, if you look at the order of magnitude here, it's nothing much, which seems to say that adding multi-determinants on the ground state does not do much to our system. However, when we look at the excited state, now the order of magnitude is higher, and now we are seeing these colorations on the diagonal that are slightly more important. So from this only picture, we can think that multi-determinants affect more the excited state than it affects the ground state. And this is something that the people who have been doing this type of materials, transition metal oxides on the ground state using DFT+U, have always been able to get significant amount of information, which might indicate that the ground state might be fine with PBE orbitals. So now we use the load wind population analysis to be able to analyze a little bit what's going on here. This is the EG states. These are the T2G states, and we compare them with various levels of PBE. So we do PBE+U, and we start looking at them a little bit, how they act. And you can see here that in the excited state, and we compare them to the multi-determinant PBE. So we're going to consider that the multi-determinant PBE orbitals is the truth, and I'm putting this between huge quotes. So remember, air quotes are important in this case. So we see here that, well, okay, this is our baseline. And we can see that first, the z-square, the z-square orbitals are absolutely not affected by the multideterminants. So whatever is going on in our system is touching parts of the EG and part of the TG. Oxygen seems also very stable, nothing much really to report for the ground states. So this is interesting to begin with. Ground states does not seem to be very much affected, and we are able to get this level of accuracy in the readings of our orbitals, and we get a lot of details. We can even pinpoint at what might be wrong in our system. When we look at the excited state, however, you can see that the value of U changes a lot of things here, and we have significantly more movements, and we have a lot of changes here. Does it mean that we understand what's going on? Not really, at least not at this level. So one thing that we do here is we see what does the multi-determinant effects. Now, everything is multi-determinant, and we see that the differences are slightly lower. So adding multi-determinants on our function, on our orbitals, reduces the discrepancies between each other. So you can see, for example, that all the oxygens, we know that the oxygens are doing the same thing. So either single determinant or multi-determinant does not affect anything on the oxygens, but there is still something happening at the level of the T2G. And of course, these are for U equals 7. Something is going on here, or at least we think that maybe the orbitals are affected differently. Same thing for the excited states. The multi-determinants seem to be fixing the orbitals, and we start having some type of similar behavior everywhere across the values of U. So is this good? Well, now if we try to understand where does the electron come from when we do an excitation in the lithium cobalt dioxide, we do the difference between the ground state and the excited states to try to see the occupations, how they work. So here we have the small crosses here are for the single determinant, and the X's are for the multi-determinant. So the multi-determinant, we can see that there is some level of transfer between the oxygen orbitals are giving an electron to the T2G and to the EG. So the band gap is not just T2G to EG. Orbitals from the oxygens are involved. Also, single determinants seem to say that only the PX orbitals are involved, while multi-determinant says, no, it's a PX, PY that are contributions, and they are contributing to multiple levels here. So, of course, because the lithium cobalt dioxide is layered, we also can see clearly that there is a breakup symmetry in the cobalts. So this is rather interesting to see that it's actually more delocalized type of transfer. It's not just one type of orbital or one type of atom that is participating to this. And okay, so does this fix the problem? Absolutely not. It makes it even worse. When we look at the band gap now, the band gap is 7. And even if we had finite size errors here, this does not justify this level of errors. So we were really not happy with this result because we thought that we had nailed it. So we need to go even beyond the orbitals that we have. So what we tried to do, because we are not able to converge completely, we decided to go to natural orbitals. And this is something that Claudia hinted at. And the group of Claudia, they reach it in a smarter way than we do because they're using molecules and smaller systems by just optimizing the orbitals on the go while they have multi-determinants and JASO and everything. In our case, what we do is that we take the PBE orbitals that we have. We start from PBE+U, and we did the trials with U equals 0 to U equals 11. And we do 5 rounds of generations of natural orbitals. So you generate the first time your natural orbitals, but of course they are incomplete because we don't have the full space. We do another selected CI on top of it, generating 5 million determinants. Now we have level 0 natural orbitals, and we repeat the operation until we reach a type of convergence of the energy. So we think that within those 5 million determinants within natural orbitals, we have captured all the physics of the problem, and all the determinants, even the ones that were not captured, are now in the system. So, okay, is this better for our systems? Now, when we look at the single determinant minus, so the difference between natural orbitals that we have generated and the PBE orbitals at the level of the ground state, we see that doing these natural orbitals just with one determinant affects all this boundary between the HOMO and the LUMO. So this is already a first indication that we are doing the right thing. Same thing happens for the excited states. Now, this block here comes from the PBE orbitals. Now, all the changes are, and it's not only one orbital that is changed. This is really the contribution of multiple orbitals that are now being changed by the natural orbitals. If now I just do the excited state minus the ground state for the natural orbitals with single determinant, now this is the picture that I want to see, which is all the changes and all the transfer happen at the edge between the HOMO and LUMO, occupied, unoccupied, or at the level of the band gap, using both single determinant and multi-determinant. So this is great. The picture of having just a random thing in the middle just jumping is not there anymore. Now we have really an edge band happening. This is great. Now, if I do the difference to try to see if really I need this multi-determinant, because the most important question now is, do I need the multi-determinant expansion, or do I just need better orbitals? Well, when I do the multi-determinants minus the single determinant for the ground states, now, yes, it touches a little bit here and it touches everywhere, but the scale is so small that it seems like doing multi-determinants does not affect the ground state, just like it was the case for the PBE orbitals. Now, exactly the same thing happens for the excited state, which was not the case with PBE orbitals, which tells me that maybe using natural orbitals is enough also for the excited state. Now, I tried to look and understand a little bit more, and we see at how, and bear with me, we still are trying to find a way to represent determinants in a fashionable way, but this is the only way that we have. So this is the first determinant, second determinant, 1 and 0s correspond to occupied and unoccupied. The first coefficient here corresponds to the coefficient or the weight, you can see it, of the ground states, and this one corresponds to the excited state. And you can see that for this one here, correspond to what we may think as a Hartree Fock, is the ground state, and all the weights of the wave function resides on that first determinant. Obviously, this determinant does not contribute to the excited state. However, the second determinant, we see that the contribution for the ground state is really minimum, and all the other determinants have really small weights. This means that the ground state is mainly described, all the correlation is in this first determinant. The second state, which is the first excited state, here, we see that actually it is not, you cannot describe the system with just one determinant. You have to use a CSF. This is a complete degenerate state. You see, this is the alpha and this is the beta determinant, and it's just a flip. In one case, you have these two degenerate states. So you cannot describe this excited state by just putting this one, because then you will have, and this basically the weight here, you need to square it. So if you do the square of this and this, you're going to be missing half the correlation if you take only one determinant. And this is something that we were not expecting doing this system. When we try to do plot all the weights and we go up to 13 determinants that we add, so the ground state, you see that either for different values of u, because we started the natural orbitals with different value of u, you see that regardless of the value of u that we start, so regardless of the quality of the natural orbitals we have, the ground state weight is more or less the same. So the different values here, the different colors correspond to different number of determinants in the expansion. So all of them are between 0.78 and 0.77 in the weight. So 75% or 76% of the correlation is in the ground state. Here, however, for the excited state, the first determinant is here. This is the ground state. If you take one determinant, you are only putting about 40% of the correlation. If you put more than two determinants, you are putting 85%, meaning that you don't care about putting 3 determinants, 4 determinants, 6 determinants, or 1 million determinants. As long as you have 2 determinants, you're good. And this is really something that we were not expecting, and we are very happy about, because then it means that we don't need to have these very large CI expansions to be able to describe our system, as long as we have correct orbitals with them. we do the same thing as the load-weighting population analysis, and you see how clean and neat everything is between different values of U starting points for generating our natural orbitals. For one determinant and for the multi-determinant that is now the truth, everything is on top of each other to some extent, to some little noise. Meaning that either you take any natural orbitals, we are converged, and our DMC calculations will be completely independent from the starting point. And this is here with multi-determinants, they are all on top of each other. So the ground state is extremely well described just with one determinant here. The populations, the physics of the problem, the orbitals are well populated just with that one determinant. Now, when we look at the excited state, it's a little bit more murkier. The reason why it's the case, it's because we did not start from the same value of U, our PBE+U, to generate our natural orbitals. So when you do natural orbitals and you start doing your rotations, basically you're not always sure that you're going to reach the same XY linear combinations. So we see differences, but actually we would need to try to track which ones are rotations of the other, but we're expecting them to be the same. So when we do now the ground state minus excited state, and this is at multi-determinants or one determinant, so we use one determinant for the ground state, and we use two determinants for the excited state, because this is very important. We need those two excited states. And we use either one and two determinants, as we call the single determinant, or multi-determinants, which have 5 million determinants. So we see that they are exactly on top of each other, except for a little bit of noise in this one here. But mainly, we see that the charge transfer or the band gap is not delocalized as PBE tries to put it. This is extremely localized, and we can really pinpoint that all the other shells are not participating. We have participation from the PY that we have this hybridation still that happens between the PYPZ of the oxygens, but mainly the contributions here we have the EG that recovers some electrons here, T2G recovers electrons, and the EG is giving them here. So this is really a nice picture that shows really strong localization of the excitation. And here we can even see that the breakage of symmetry, which cobalt atoms are going to be involved in this type of charge transfer, which was a picture that we were not able to get before. When we use now these natural orbitals to do the band gap using diffusion Monte Carlo, so we inject this determinants in diffusion Monte Carlo, now we are significantly closer to the experimental value, and the remaining error that is here is just due to the finite size effect, because we started from a primitive cell of 3 cells instead of going to larger cell. So I hope that I convinced you that we are able to generate very, very complex trial wave functions for small systems, but more than that, we're able to find that not all the systems are multi-reference. Sometimes just with multi-determinants, just having one or two determinants describing the system, we are able to get significantly more physics and accuracy than going very crazy large and with bad orbitals. The single determinant, I still want to make sure that I did not go too hard on PBE and PBE+U for the ground state, but I think the PBE+U is still enough to describe this class of materials correctly. But we need to be able to fix bad orbitals, or the starting point remains the biggest issue that we have. We can now have a deeper understanding of the physics of the chemistry of a problem, but we need to improve the trial wave function and go beyond just pure simple DFT orbitals. And on that, I think I spoke very fast, but I'm happy to have more time for questions. I would like to thank the Center for Predictive Simulations of Functional Materials that is led by Paul Kent at Oak Ridge, my colleagues from the CPSFM for all the conversations, and the time at Argonne through the InSight project. If you have any questions.